So now that we've looked at weak acids and strong acids, we're now going to look at strong bases. Now, when we're doing pH calculations for strong bases, we don't have to use ice charts. And we don't have to use ice charts because 100% of the strong base is going to dissociate. However, I like to show the ice chart just because it makes it a lot easier for me, so I'm going to show the ice chart right now. Okay, so let's look at a problem. It says, what is the pH of a solution of 0.040 molar calcium hydroxide? Okay, so I'm going to show the dissociation of it. So it's going to be calcium hydroxide decomposes into calcium ions and 2 hydroxide ions. I'm going to create an ice chart. My initial concentration of calcium hydroxide is 0.040. The initial concentration of calcium and hydroxide are both 0. Okay, so the change, because this is a strong base, the change is going to be negative 0.040. The change for calcium is going to be plus 0.040. And then because for hydroxide there's a 2 coefficient, it's going to be plus 0.08. Okay, so at equilibrium, your concentrations would be 0, 0.04, and 0.08. Okay, to find the pH, since I have the concentration of hydroxide at equilibrium, I need to first find the pOH. So the pOH is going to just be the negative log of 0.08. So that gives me 1.10, which means the pH is going to be 14 minus that, which is going to be 12.90. Now notice I have 2 decimal places, and I have 2 decimal places because they're 2 sig figs in the values I'm using. Just like with weak acids, we have a generic formula for the dissociation of weak bases. And in this case, a weak base is represented simply with a B. When it reacts with water, remember it's a proton acceptor, so it becomes HB with a positive charge, or 1 more than it originally had, plus hydroxide, because hydroxide lost its proton to the base. Now, again, just like with weak acids, we can write the equilibrium expression. In this case, it's going to be your BH or HB plus, so your conjugate acid times the concentration of hydroxide all over the concentration of your base. Remember again that water, since it's a pure substance, we don't include it in your equilibrium expression. And again, your Kb is now your base dissociation constant rather than your acid dissociation constant. So in this reaction, I have ammonia reacting as a base. Therefore, in this reaction, I have ammonia as my weak base reacting with water, which is going to serve as my acid in this problem. Remember, double arrows because it's a weak base. Ammonia is going to accept the proton that water gives it, so it becomes NH4 with a plus 1 charge, and water loses its proton, so it becomes hydroxide. Now this problem is now going to be identical to the weak acid problems we previously performed. So I got to write out my ice chart. I have a concentration of 0.15 molar NH3. Remember, since this is a pure liquid, I'm actually not going to be looking at water at all, so I can just ignore that. I start with no ammonium and no hydroxide. I do know that the change is going to be minus X for ammonia, so the equilibrium concentration is going to be 0.15 minus X. I know that this is going to be plus X, and this is going to be plus X here. And so my equilibrium expression is going to be X times X, which is X squared, all over 0.15 minus X, and I'm going to set that equal to my Kb, which in this case is 1.8 times 10 to the negative 5th. I'm going to assume that my X is small enough that it won't affect my equilibrium concentration of NH3, so I'm going to ignore it to make my life easier. So X squared equals, when I multiply 0.15 by 1.8 times 10 to the negative 5th, I get 2.7 times 10 to the negative 6th. Okay, and then I need to find the square root of that, so my X is going to end up being 1.6 times 10 to the negative 3rd molar. And so this is actually going to be my concentration. My X is my concentration of my hydroxide ions. And so what I can actually do is I can take that and plug it into my formula for POH. I'm going to find the negative log of the 1.6 times 10 to the negative third. Okay, and when I do that, I find that my POH equals 2.8. Now, I'm actually not interested in POH. I want to find my pH. So 14 minus that value gives me a pH of 11.2. And that is my final answer. In this lesson, we're going to look at the relationship between Ka and Kb, and we're also going to be introduced to the common ion effect and then also look at buffers. So to begin with, we're going to first write the acid dissociation reaction for ammonium ion. And so in this case, ammonium is going to serve as the acid, so the reaction would be NH4, and it's going to produce NH3 plus hydrogen ions. Now you could also write this with water to produce hydronium ions. To write the base dissociation of ammonia, NH3 is going to react with water and it's going to produce ammonia and hydroxide. So there's your reaction there. So if I wanted to take these two reactions and add them together to get the overall reaction, what you actually will find is that it ends up being the reaction for the autoionization of water. Here it doesn't show the second water on the reactant side, but if you imagine it, then instead of hydrogen ions, it would be hydronium ions. So that is the autoionization reaction of water, which tells us since we added these two reactions together to get that third reaction, the autoionization of water, when you add two reactions together, you need to multiply their equilibrium constants together, and therefore that tells us that Ka times Kb, which are the equilibrium constants for those two reactions, when you multiply them together, that actually gives you your Kw. So that formula there, Ka times Kb equals Kw, that allows you to relate Ka and Kb. Another important thing to keep in mind, since your Kw is 1 times 10 to the negative 14th, if you take the log of each of these values and simply add them together, so the pKa plus the pKb, that will give you your pKw, which simply equals 14. So that further helps you in relating Ka and Kb to one another. So what we're going to do right now is we're going to see how we can take Ka and actually determine the strengths of acids and bases based on values that are given to you in this example problem. So here it tells you that the Ka of acetic acid is 1.8 times 10 to the negative 5th, and the Ka of hypochlorous acid is 3 times 10 to the negative 8th. Well, based on our basic knowledge of Ka, I know that acetic acid is a stronger acid simply because more of it dissociates, therefore giving it a larger Ka value. Now, what we need to do is calculate the Kb for their conjugate bases. And so all you need to do is take your Ka times your Kb, set that equal to the Kw, and that will enable you to calculate the base dissociation constant. So for the acetate ion, I'm going to take 1.0 times 10 to the negative 14th and divide it by the 1.8 times 10 to the negative 5th. What I end up getting for the Kb is 5.6 times 10 to the negative 10th. If I do the same thing, if I take the Kw, which is 1 times 10 to the negative 14th, and divide it by the Ka of hypochlorous acid, that gives me the Kb of its conjugate base, which is 3.3 times 10 to the negative 7th. Therefore, I know that ClO minus, which is the conjugate base of hypochlorous acid, is a stronger base than the acetate ion. And that actually makes sense because remember, the stronger an acid is, the weaker its conjugate base is. So since acetic acid is stronger than hypochlorous acid, that means that hypochlorous acid's conjugate base would be stronger. So we're able to calculate Ka and Kb. If we know one of them for either an acid or a base, then we can calculate that other value for its either conjugate acid or conjugate base by using the relationship Kw equals Ka times Kb.